Welcome back everyone. In this lecture we will recall some basic results from elementary number theory. So we will record all the results that are needed from elementary number theory in this lecture. So let us start with fixing some notation. So this is something we already done, but anyway let's recall. So we denote natural numbers by n, so which consisting of all positive integers, and then we denote z plus by all non-negative integers including 0, and then we denote z by set of all integers. So this is 0 plus or minus 1 plus or minus 2 and so on. So this is the set of all integers. This is the set of all natural numbers. So this we call it non-negative integers. Okay, so first we define the divisibility. So all of you must be knowing all this, but anyway it's good to recall. So given two integers a b with b non-zero. So let's say given two integers a b with b non-zero. So we want to say that b divides a. So when we can say b divides a, so this is symbolically we write this b vertical line a. So this should be read b divides a. So you say this if there exists another integer q such that a equal to qb. So this is the symbol that we will be using always. Okay. So now there are some elementary properties of this divisibility. I will list all these properties. I will not prove them. So I will leave them as exercise. So here is the exercise. So these are all some elementary properties. You start with three integers a, b, c such that a and b are both non-zero. So let a, b, c they are integers such that b and c both are non-zero. So in one line we can write ba is non-zero. So the first property, if a divides b and b divides c, so then one can conclude a divides c. The second property, if a divides b and a divides c, so then we can take any integral combination of b and c, so that should be divided by a. So then a divides bx plus cy for all xy integers, and this can be extended to any finitely many number of integers. So maybe I will write it as a third. So if a divides bi for I equal to 1 to k, so then if you take any integral leading combination of this bi, so then a divides summation xi bi for all xi in z for I equal to 1 to k. So and one of the important property of this divisibility, if a divides 1, since 1 is being unit inside your set of integers, so then this should immediately imply a is either plus or minus 1. Okay. So from this you can conclude that if a divides b and b divides a, so then they differ by just this plus or minus 1. Okay. The another property, if m is non-zero and a divides b, so then we can take multiple of A and then multiple of B. So, then this MA should divide MB. So, these are all some elementary properties of this divisibility. So, this you must have done it in the first course in elementary number theory. So, I am just recalling it here. So, now we will actually see an important result that you prove in elementary number 3 called division algorithm. Okay. So, I will actually give you a proof that is somewhat more algebraic, okay, in some sense that uses the coset property of the integers. Okay. So, let me first state the result and then I will give you the proof. Okay. So, here is the division algorithm. So, division algorithm has many different proofs. Okay. So, each proofs actually kind of involves some properties of integers and natural numbers. Okay. So, and then so this particular proof I would say it's a very important proof that you will be this idea will be repeating again and again in both in group theory as well as ring theory. So, okay. So, what is division algorithm? You start with two integers a b with b being positive integer. Okay. So, then basically you want to divide a by b. So, then there will be a quotient and the remainder. Okay. The remainder you can always choose to be less than b. So, that is what division algorithm guarantees. So, then there exist unique q and r from Z such that this a can be written as qb plus r with 0 less than or equal to r less than b. Okay. So, you divide this a by b, then you get this quotient q and then this remainder r. So, this is called remainder and this is called quotient. Okay. And these are both these numbers are unique, satisfying this property. So, the uniqueness is fairly obvious. Okay. So, this is something I have done it in the earlier lecture, but I gave different proof for this fact. But here I am going to give another proof which actually kind of understands the coset that you actually define using A and B. Okay. So, what is the idea of the proof? So, the idea of the proof to look at the following coset. Okay. So, this is something I already introduced in the previous lectures. Okay. So, what is the coset that we are interested in? So, you take this all possible combinations like this. Okay. Consider this S. So, what is this S? So, this S is consisting of you start with A and then start adding and subtracting B. Okay. A plus B, A plus 2B and so on, and then A minus B, A minus 2B and so on. So, indeed it is an infinite subset of integers. So, these are all lie inside each other. So, your moment thought will tell you that. So, all we do is we take A, we just add all multiples of B, integral multiples of B. So, that is what we are doing. Okay. So, we added B, 2B and then minus B, minus 2B and so on. So, in particularly this S is same as A plus Z times B or B Z. Okay. So, this is recall, this is exactly equal to A plus Bx where x is coming from Z. So, this is coset with respect to this subgroup Bz. This is something we have seen already. So, this set, so I will explain later why I want to call it as coset, but anyway this is set something I introduced already, and then we saw that some arithmetic can be done between these sets. So, now if you take this set A plus Bz, okay. So, this is possibly it is actually consisting of infinitely many integers. So, your moment thought can tell you that it will definitely have infinitely many positive and negative integers. Okay. So, I will leave it to you to check, okay. This is something I will leave it to you to check that S intersection N will be non-empty, okay, and it could be empty in only one case when B is 0 and A is negative, but to begin with we assume that B is already positive. Because B is positive, so S intersection N must be non-empty always. So, in particularly we can talk about, because this N with respect to the order that we have on N, it is actually a well ordered set, okay. So, N with respect to the order that we have is, with respect to this is well ordered. So, what is the meaning of well ordered? So, given any non-empty set, okay, if you start with A, which is a non-empty subset of N, then this A has minimum. So, there exists A in A such that this A is less than or equal to B for all B in capital A, okay, and we can prove that this is unique, such A exists. So, this is the property of well ordered sets, okay. Now, using this property, you can see that if we take this S intersection N as capital A, this is a non-empty subset of N. So, there exists some R, okay, inside this S intersection N, and this R is actually smallest non-negative integer in this set, okay. So, this is the smallest non-negative. So, okay, so we can make it actually because the remainder could be 0. So, in that case we have to allow 0. So, I can make this N to be Z plus, okay, and it is not hard to replace this N with Z plus. So, there is no harm. So, now with now if we take this S intersection Z plus, so then you get this R, which is the smallest non-negative integer in this. So, this is the smallest non-negative integer in S intersection Z plus. So, that is the property of the sum. So, then it is clear that there exists Q such that R equal to A minus Q B for some Q inside Z, okay. So, that is more or less by definition, because S is defined to be just A plus B Z. So, now you have this R, then it is clear that this is the R that we want, okay. So, it is not hard to check this A is equal to QB plus R, and this R should satisfy this property. It should be less than B and it is non-negative. So, non-negative by definition, and it is supposed to be less than B, otherwise you will be able to subtract B from R. So, that will give you contradiction to the choice of R. So, let us try to do, okay. Suppose this does not happen, if R is greater than or equal to B, so then it is clear that R minus B, okay. So, which is of the form A minus Q plus 1 B. So, this is still in S and this is greater than or equal to 0, okay, but R minus B is strictly less than R, which is a contradiction, because R is the smallest non-negative integer inside S intersection S plus. So, that forces that this R is less than B. So, that means 0 less than or equal to R, 0 less than B, it is proved, okay. So, the uniqueness of this R and Q, it is already proved in the previous lectures, you can actually check there, and it is not that hard to prove, okay. I will leave it as exercise. So, prove the uniqueness. So, prove the uniqueness of R and Q, okay. So, now we have the division algorithm. This division algorithm is somewhat very powerful in order to compute what is called greatest common divisor. So, before actually getting into that algorithm, let us first define what is this GCD, okay, GCD. So, this is, here is the definition. So, GCD means greatest common divisor. Okay, what is the meaning of GCD? So, you start with two integers, not both of them are 0. So, let A B they are integers such that A B is not equal to 0 0. That means both are not 0. So, then the GCD of this A and B. So, shortly it is denoted by GCD of A comma B. So, this is defined to be, so this is defined to be the largest integers. So, integer D such that D divides A and D divides B. Okay. You look at all possible common divisors and you pick the largest one. So, that is called greatest common divisor. Basically, you divide this word into two, you look for all common divisors and then take the greatest among them. So, that is called greatest common divisor. So, we do not really define GCD of 0 comma 0 because that does not make any sense, because any integer can divide 0 comma 0. So, there is no greatest among the common divisors of 0 comma 0. So, it is not defined. So, now here are some basic properties. Okay, this is something I will leave it to you to check. So, these are not very hard to check. So, the very first property, so the GCD of A comma B, this must be always positive. Okay. So, you can easily prove that GCD of A comma B is same as GCD of the absolute value A and absolute value B, which is also same as GCD of A comma minus A comma B and then GCD of A comma minus B and then GCD of minus A comma minus A comma minus B. So, the GCD of all these numbers are same. This is something easy to verify. And then if you take GCD between A comma 0, so then that must be the absolute value of A. Similarly, if B divides A, so then the GCD of A comma B must be the absolute value of B. So, GCD must be always positive. Okay. So, now one of the important property of GCD, okay, so you can always write GCD of A comma B as integral combination of A and B. So, that is something I will prove. So, before that let us again look at one more property of GCD. So, if A and B are integers, not both are 0, so then what one can prove, if you compute GCD of AB, then it is same as GCD of A plus Bx comma B. So, this just follows from the divisibility properties. Okay. Suppose if you call the GCD of AB as D and then if you call this GCD of A plus Bx comma B to be D dash, so then you can easily prove that D divides A and D divides B will imply D divides A plus Bx and D divides B. So, that will force this D is less than or equal to D dash. And similarly, you can see that if D divides A plus Bx and D divides B, then D must divide A plus Bx minus Bx. So, that means D will divide this. Okay. So, that will force that D dash is less than or equal to D. Okay. Similarly, you can prove that D dash is less than or equal to D. So, that will imply D equal to D dash. Okay. So, these are all some elementary properties, that is why I am not going into very much details. So, but this is one of the important property of GCD. So, if you take GCD of AB, then that is same as GCD of any like this combination A plus Bx comma B for any x in Z. So, now using this, so I will state a theorem. So, we will prove the following theorem, which is important. So, let A be integers such that A comma B both are not 0. Okay. So, then there exist xy in Z such that this GCD of AB is given by AX plus BY. Okay. So, GCD can be always written as integral linear combination of A and B. So, that is what this theorem says. Okay. So, this theorem can be proved in two different ways. So, one can use this Euclidean algorithm to compute GCD. So, that uses actually division algorithm. Okay. So, I will leave it to you to think about that. I will just sketch how it works. So, this is called Euclid's algorithm to compute GCD. So, basically what you do, you repeatedly use division algorithm to obtain a series of equation as follows. You start with A and then you can write A as Q1B plus R1. So, with this R1 being less than B. So, then you just repeat this with B and R1. So, B can be written as Q2 R1 plus R2 with 0 less than or equal to R2 less than R1. So, now note that the GCD of A comma B is same as GCD of this A minus Q1B comma B, okay, because I can take any combination here. So, this is what this last thing says, I can take any A plus Bx and I can still don't change the GCD. That means GCD of A comma B is same as GCD of B comma R1. Similarly, you can, if you think about it, the GCD of B comma R1 is replaced by GCD of R1 comma R2. Okay. So, every time when you actually apply this division algorithm, you replace the tuple and then you are actually somewhat bringing this B down. Okay. So, for example, so you started with the B and then you are going down to R1. So, you start with this tuple AB and then you are going down to B comma R1 where R1 has smaller value than B. So, now you see that you also replace this with some new tuple. So, this R1 now you divided by R2. So, then this R1 can be written as some Q3 R2 plus R3. So, with this 0 less than or equal to R3 less than R2. So, then the GCD of R1 comma R2 will be same as GCD of R2 comma R3. So, every time what we do, we replace this number by something smaller. So, obviously, this algorithm stops at some finitely many steps and then you exactly get some equation like R j minus 1 equal to some Q j plus 1 R j. So, then the GCD of A B will be exactly equal to R j. Okay. So, now you know that this R j minus 1 will satisfy something like this, R j minus 2 equal to Q j R j minus 1 plus R j. So, with this 0 less than R j less than R j minus 1. Okay. So, now you can see that if you are interested in computing R j is nothing but R j minus 2 minus Q j R j minus 1. So, using this, replacing R j by R j minus 2 minus Q j R j minus 1 and then replacing this quantities back in the previous equation and so on, you will see that there will be some x and y such that R j will be equal to A x plus B y. So, this is just the outline of Euclid's algorithm. So, basically every time if you are interested in computing GCD between A B, you replace this tuple A B by some new tuple B R1 where the value of B actually goes down by R1. Okay, without loss of generality, you can assume A is greater than or equal to B. Otherwise, yeah, this is because GCD of AB is same as GCD of BA. So this algorithm works fantastically, and this proved to be very nice algorithm to compute GCD. Okay, so for example, so here I will do one example. So you can start with very large numbers, but then if you use this division algorithm, then quickly you will actually get into something very small. Okay, for example, if you are interested in computing GCD of 841 and 160, so then what happens if you use this algorithm, you can see that you write 841 as multiple of 160, so that will be 5 times 160 plus 41. So now you can see that the GCD of 841 160 went down to GCD of 160 comma 41. Okay, but again if you use division algorithm for 160 and 41, then you can write this as 3 times 41 plus 337. So then now you can see that the GCD again went down to 41 comma 37. So now you can again use the division algorithm. So then this 41 can be written as 37 plus 4. Okay, and then if you use 37 will be written as 9 into 4 plus 1, then 4 will be just 4 times 1. So that means the GCD of this is same as GCD of 37 comma 4, which is same as GCD of 4 comma 1, which is 1. Okay, so this is how you compute the GCD. So quickly this algorithm escalates and then it brings you down to small numbers so that you can actually compute this GCD. So this proof, of course, very important proof from the algorithmic point of view, but from theoretical point of view, so I will give you another proof which actually kind of looks at all possible linear combinations of A and B and then picks something from that combination. Okay, and then the smallest possible positive integer in that combination will serve as your GCD. Okay, so here is the second proof. So what is this proof? So this proof actually just to look at all possible combinations. So take S to be basically AEZ plus BEZ. So what is this? This is AX plus BY where XY comes from integers. So a moment thought can tell you because both A and B are non-zero. If they are 0, then S is 0. Okay. So because one of them at least non-zero, then you can see that this S must be infinite. It contains both positive and negative integers. Okay, I will leave it to you to check. So in particularly what you can do, you can actually prove that S intersection N will be non-empty. Okay, so this is something I will leave it to you to check. So you can check by, for example, case by case. So the important point here, this AEZ plus BEZ, okay, this is not some random subset of Z, it is indeed a subgroup. So this is something you can directly check. So this is indeed subgroup of integers. Okay, we have already seen what are all the subgroups of integers. The subgroup of integers must be of the form DEZ for some D. Okay, so in particularly this also must be some DEZ. So that is the D that we are actually looking for. So we always choose D to be positive integers so that it generates. Okay. So okay. So what is the D? Indeed, the D is the smallest possible positive integer. Okay. So then take D inside this intersection N. So this is the smallest possible positive integer. Okay, such a D exists because S intersection N is subset of N is well ordered. So now by definition D can be written as A x naught plus B y naught for some x naught y naught inside integers. Okay. So, now we need to prove that this D is indeed GCD. There are two things to prove. It is the largest common divisor. Okay. It first of all common divisor and it actually largest among them. So, why it is common divisor? Let us prove D divides A and then I will leave it to you to think about D divides B. So, D, suppose if you want to prove D divides A, then the important thing to use is again use division algorithm. Okay. Without division algorithm we can't prove anything. So, to prove D divides A, so look at A equal to some QD plus R using the division algorithm. So, it is enough to prove this R is 0. So, this R will satisfy the property that it is less than D and greater than or equal to 0. So, now you can see that this R is nothing but A minus QD. So, since A is inside your S, okay, and QD it is also inside your S. So, this combination should be inside your S. So, this is in S, this is in S. So, if you add them it should be in S. Okay. This is the property of subgroup. So, that is what we are using now here. So, that means R is in S, but what is R? If you write R, this is 1 minus x naught times A minus B y naught. So, which is inside S. Okay. So, this R is smaller than D. So, but D is the smallest positive integer possible. So, that forces that this R is 0. Okay. So, that means D divides A. So, similarly, you can prove that D divides B. Suppose if you have some other divisor, for example, if you take GCD of AB, so the GCD of AB it is the largest common divisor. So, it has to be greater than or equal to D, but D is actually combination of A and B. So, D equal to AX naught plus BY naught. So, that means the GCD of AB must divide this AX naught plus BY naught which is D. So, that will force that the GCD of A comma B is less than or equal to D. So, that means D must be equal to the GCD of A comma B. Okay. So, this actually gives another proof using the property that this AZ plus BAZ is nothing but a subgroup of Z. Okay. So, this also gives us immediate corollary that the greatest common divisor of A and B is the smallest positive integer which can be written as a Z linear combination of A and B. Okay. So, the first proof, the Euclide's algorithm is more practical algorithm. So, it gives you algorithm to compute the GCD of A and B, but the second proof is more theoretical proof. It actually uses the correct property of this set AZ plus BZ in order to find out the combination. Okay. So, now it is not hard to generalize GCD for any given finitely many number of integers, not all of them 0. So, you can talk about GCD of A1 etc. AN, and then I will leave it to actually prove that given this A1 etc. AN the GCD. So, then there will be a combination like this. There exists xi such that A1 x1 plus etc. AN x1 will be the GCD of this. And generalizing other properties of GCD to this finitely many integer is not very hard. I will leave it to you to think about it. Okay. So, I will continue with this again elementary property of elementary number theory results in the next lecture, and then slowly we will move to like cyclic groups and other finite abelian groups. Okay, I will stop here. We are running out of time. Thanks.